recently joined speaker between two of the groups at the Newton right now, from ANU and also the institute I most want to spend time at, the Bodega Bay Institute with Vaughn. Anyway, thanks very much, Scott.
Thank you. Yeah, so thanks everyone for coming along to hear a talk that is maybe a bit outside the scope of everything else going on this week. And I also want to thank you preemptively for your patience today, because I have to admit I'm a bit worried about this talk and I'm not quite sure what's going to happen. While Dorothy and I have very kindly given me this chance to speak jointly between the two programs, I wonder a little bit whether I'm the sacrificial lamb so that they can write that paragraph about interactions between the programs. So Di in particular suggested that I could try and talk about connections between the theory of subfactors and link homology. And I tried to insist that there were no connections. But I'm still giving this talk. And so you're going to need to be patient, because my plan today is to talk about some of the resemblances between things you see in studying subfactors and things you see in studying link homology. I'm then going to have a little sort of honest moment in the middle of the talk when I'll try and explain why these are superficial resemblances and you probably shouldn't get excited about them. And then I'll just be completely irresponsible and have a sort of fantasy session at the end where we try and make something out of these resemblances. It's fantasy. Don't get your hopes up. Okay. That all said, maybe this sounds a little bit ungrateful towards Dorothy and Di giving me this chance to talk about it. I've actually really enjoyed trying to think of some connection between the two subjects to talk about today. And I had a very enjoyable morning with Paul Wedrick this morning. Maybe a new categorification or something interesting. Anyway, let's go. So let's start right at the beginning. So I'm going to roughly give you an ahistorical version of how the Jones polynomial was discovered in the world of subfactors, and then we'll go on and talk more about Temperley-Lieb. So I want to consider at the beginning just an inclusion of rings. Which I'll tend to call A and B. Okay, maybe just a unital inclusion of rings, nothing else for now. And what I want to start by doing is we can think of B, the big ring, as this guy, which means we're thinking of B as an AB bimodule. Okay, we're just remembering the multiplication by the smaller algebra A on the left and the multiplication by the whole ring B on the right. So this is B as an AB bimodule. And now what I want to do is start looking at tensor products of this bimodule with itself over the rings A and B. So we have, we can take this guy, and we can also think of it the other way around as a BA bimodule. And so then we can tensor those guys together. The resulting thing still has two actions of A on either side. And of course, this is just B itself, thought of as an AA bimodule. Okay? And a map, of course, we can just take the smaller algebra A, thought of as an AA bimodule, and just include it up into B, which, just remember, I'm going to want to think of as this bimodule sort of tensored with its dual bimodule, be thought of as a bimodule the other way around. Okay, what else do we have? Well, the other thing that we get for free just by thinking of an inclusion of rings is, what do we have? Well, we can take B and we can tensor it just over A with B and think of this gadget that results as some BB bimodule. This is now just something probably genuinely new and much bigger than than either A or B itself. But there's obviously a map here back to something more familiar. We can go back from this guy to B as a BB bimodule just by multiplying the two elements using the multiplication in B. Okay, so you should think of this thing as given by, it's spanned by pairs of elements in B up to some relation that you can move elements of A back and forth between the pair, and you can just multiply the pair. That's well defined on this tensor product. Okay. So let's draw some pictures for these. So the first one, just the inclusion, I'm going to draw, actually, I'll try and be consistent about using colors here. So green, for as long as I can remember to use green, is going to represent this bimodule, that B is an AB bimodule. And I'm going to draw it like this, as a little cup that's unshaded on the outside and shaded on the inside. So what there are no points at all down here, and it's unshaded, and I want you to always interpret that as the small algebra A as a bimodule over itself. And then up here, when we read across the top here, what do we see? We see unshaded, then the bimodule, then shaded, then the bimodule, then unshaded. And so that's why this picture is meant to represent a picture, a morphism rather. Sorry, did I do this the wrong way around? No, there we go. As a map from the small ring to B tensor over B with itself, thought of it again as an AA bimodule. So this is the inclusion. And then the other guy maps the other way. Now it's a map of BB bimodules. I've already forgotten, sorry. There's the green string for the bimodule. But now the picture that I meant to draw associated with the second map that I wrote down there is this thing that's shaded on the outside because it's a map from some BB bimodule. The shadings on the outside tell you the B action. It's only tensored over A because there's an unshaded region in there. And then it's this map by multiplication. Okay. So that's all that we get for free, thinking in this ridiculously general context of just an inclusion of rings. So let's start adding some structure. So suppose first A and B are von Neumann algebras. Now I'm not going to use very much except as black boxes facts from von Neumann algebras, but since this is a conference very far from being about von Neumann algebras, let me at least tell you very, very briefly what this is. So in particular, well, both A and B, but I'll just say it for B, this means maybe we're thinking of B as some ring of bounded operators on Hilbert space, so it's some subalgebra of V of H, with the property that if you look at the double commutant of B, so the commutant of B would just be all the bounded operators that commute with everything in B, and the double commutant is everything that commutes with everything that commutes with everything in B. Okay, so we can ask that B double prime equals B. Certainly B is a subring of B double prime, sort of just tautologically in the definition, and we can ask that, and that's what we mean by von Neumann algebras. Let's ask for some more. Let's also ask that they are tracial. So here we have a map, trace, from the big algebra back down to the complex numbers. So that, what do I want? Well, I want it to behave like a trace. That is, it doesn't depend on what order you put the multiplied arguments inside of it. And I want it to be a normalized trace in the sense that trace of the identity in my algebra should be 1. Okay. So right away here I'm asking something perhaps a bit strange. I mean, you can't just take all of B of H anymore. There's no sensible trace you can put on all of B of H so that the trace of the identity would be 1. And of course there's some technical conditions here which well, I want a sort of positivity condition that trace AA star is non-negative with the trace of that equals 0 only if A was 0, and I need some sort of continuity condition. If I've got some net converging in some particular way, then the traces converge as well. But none of that's going to matter really in what follows. I just wanted to hint at the fact that you've got to do some work to get the next things out of this. Okay, so with these extra assumptions, we suddenly get a whole lot more. So in particular, we get a map that takes us from B, tensored over itself, thought of as an AA bimodule, back down to A as an AA bimodule. And this is called conditional expectation. And just to give you a little glimpse as to where this comes from, what you do is you take that trace you've got over here, and we think of A and B as acting on not whatever arbitrary Hilbert space over here, H, we started with, but a particular nice Hilbert space that we build out of the trace, which is usually called L2 of B, or maybe it should be even called L2 of B comma the trace, which is just the, well, on B, you can define an inner product given by multiplying your two elements with taking an adjoint in an appropriate place and then taking trace of this. This really is an inner product by some of the things we assumed over here. And now you can just take the L2 completion of this vector space B with respect to this inner product and get some Hilbert space. You think of these guys as acting on this Hilbert space, so they're now not acting on some arbitrary Hilbert space, they're acting on this guy. And then you look at just the orthogonal projection of L2 of B down to L2 of A with respect to this inner product. And then just think of this, restrict this to actually the map on B. You have to do a little lemma to see that the image is actually A, and this is our map here. Okay. There's a fair bit of work in there. If you're interested, by the way, in understanding some of the details of what I say in these 5 minutes, David Pennies gave an excellent series. Well, I wasn't here for it, but I assume it was excellent. I looked at his notes, and they were excellent. A series of introductory lectures on exactly this material 2 weeks ago, so it's on the INI website in not too long. Okay, so we get this, and of course there's a nice diagram for this. This has two guys at the bottom. It's a map from B as an AB, tensor B as a BA, to just A as an AA. And then we also get one more map that's exactly the fourth one in this setup. We can go from B as a BB to be tensored over A with B. And I'm really not going to say anything about where this one comes from, as it would take us quite a while, except out of the words Pimson-Popper bases, and leave it at that. Okay. So with this extra assumption that our rings are really nice, we get a whole lot of extra maps. And the important thing is that these satisfy the relations you might expect. In particular, green string. You can have a green string with a little zigzag in it. Maybe it's shaded on one side. And so this is now built out of our inclusion map and our multiplication map. So this one is actually a pretty easy one. This is all built out of things we understand very well. And in fact, you can see for yourself that this is true even just when A and B are rings. There's nothing special in this identity. But there are a bunch of other identities as well. For example, we could have had this one, the same zigzag, but now shaded on the left. And this identity, I think, is probably much more profound. Let's just have a quick look at where it comes from. Because this one involves our map coming from these bases and our map coming from the conditional expectation. So we're really going to have to think about subfactors for a bit to prove this identity. And there are finally two more. The zigzag can go the other way, and those are two more independent facts about this little collection of diagrams we've built. Okay. Maybe as an example, let me just sort of I sort of want to squeeze it right in this board here. So let's have a little red box with a tiny example, if you want to think about it. We're welcome if you wanted to just think about the complex numbers sitting inside 2x2 matrices as our inclusion of rings at this point. On the trace here, I want you to use the normalized trace, so half the honest trace of this matrix. and then we can say, color coding, we can say what these maps are. So this guy, of course, is just meant to be a map from 2x2 matrices back down to 1x1 matrices, and that's actually just the honest, well, normalized trace. And then the other guy is send some 2x2 matrix to, where is it meant to be going to? This is meant to be going to B tensor B over the complex numbers, so that's just going to be 4x4 matrices, and it ends up just being this map here. And you can go away if you want a little exercise rather than listening to the rest of my talk. You can go and check these zigzag relations hold. There. Okay, so what have we done at this point? We've built a little two category. Which I'll call, is called the Temperley-Lieb two category. So the objects in this two category, so it's a two category, so we have objects and one morphisms and two morphisms. The objects are the two rings, A and B. The morphisms are maybe some line with some green dots on it, which are alternately shaded and unshaded between them. And of course, you're thinking of this one morphism here as being just the tensor product of copies of this bimodule B either way around. And the two morphisms are just all of the things we can build out of these four fundamental guys. So for example, a morphism from something like this to another thing like this will be some planar diagram that can be built out of cups and caps with shadings in between. Okay. Well, there's a few more relations that turn up here and that turn up naturally from this description here. Let's say we look at this morphism here. Well, what is this? This is just the inclusion of A into B, and then the conditional expectation of B back down to A. So can people over this side of the room see this board, or is it okay? Yeah. So this is just the map from A into B as an AB bimodule, including, and then projecting back to A as an AA bimodule. And since we constructed this just as this kind of orthogonal projection, this map here is actually just the identity, okay? The circle the other way around well, what is this? This is a map from B as a BB bimodule to B as a BB bimodule, and it's some complicated thing built out of the scary parts of this construction that I haven't given the details of. But what we can say is that if B is a factor, which is just a fancy way of saying that it has trivial center, it's a von Neumann algebra with trivial center, then this map, whatever it is, has to be a scalar multiple of the identity. All right? It's a map from B to B that commutes with all elements of B. Okay, so it's a scale. And it's called the index. There you go. Of the inclusion, for sort of measuring the size of B relative to A. Okay, so with all of that set up and in hand, let's just quickly rediscover the Jones polynomial following Jones. And maybe I should just add a little explanation here that this is a slightly ahistorical version of the discovery of the Jones polynomial. Initially, he wasn't thinking in terms of this two category that was built out of bimodules and tensor products of this basic bimodule. He was working in something called the tower of relative commutants. Everything is slightly different, but somehow the proofs and the constructions are isomorphic. This is really just a relabeling of all the words that he used in discovering this stuff. Okay. Well, it's slightly easier. Oh, sorry. Let me put a big giant exclamation mark here, sort of warning you that this taking the easy way here is probably a terrible, terrible idea. If we renormalize some of our morphisms here, let's just change by some scale this guy and this guy. Notice that as long as we change these by, we multiply this by x and this by x inverse, all of these string straightening relations will still hold if they held before, so we're okay. And we'll choose how to renormalize them so that both of the circles, whether shaded inside or outside, are equal to some number. Okay? So this is delta times the unshaded empty region and delta times the shaded empty region. So we just rescale these by the square root of whatever that index happened to be. Okay. And then define a crossing. So maybe this is, we're doing knot theory for checkerboard shaded knots here, although with these renormalizations we've just made, the checkerboard shading doesn't matter at all. And, well, we can put in some coefficients here, but let's put in A and A inverse. And of course, a story that basically everyone in the room, I'm sure, has seen, or, well, maybe, okay, I don't want to embarrass you if you haven't seen it, but you should have. As long as this parameter A is picked so that it satisfies this equation, this gives a knot invariant, and it's the Jones polynomial in some set of conventions. Okay. So that's all very well, and it's sort of meant to be a quick introduction to how Temperley-Lieb first showed up in the world of subfactors. So now I need to pause and do something completely different, which is to say a little bit about link homology, where I will be probably even maybe even briefer and less helpful than how I've been so far, on account of you guys all being topologists and already knowing everything about link homology. Link homology happens because Temperley-Lieb can be categorified. So I introduced it, Temperley-Lieb, as a 2-category. So obviously here I'm meant to be telling you some 3-category, and let me briefly do that. And the version that I'll briefly give is the picture that Dror Banatan described, because it's very pretty and quick to do. So Banatan told us a 3-category. So if I'm going to specify some 3-category, I need to tell you the objects, I need to tell you the 1 morphisms, I need to tell you the 2 morphisms, I need to tell you the 3 morphisms. The objects are very boring. There's just one of them, so I'll call it star or turtle or whatever you like. The 1 morphisms will be intervals with some finite collection of points marked. So roughly the set of 1 morphisms is more or less like the natural numbers. All that really matters is how many points we drew. The 2 morphisms will be, maybe I can keep to my color coding. These dots should be green, I guess. The 2 morphisms will again be Temperley-Lieb diagrams. So this is some morphism from 4 points to 6 points. But I just want to emphasize here that at this level there are no relations. For for example, the circle here is just a circle, and even there's no relation imposing isotopy. We can just say that two isotopic diagrams are different and unrelated when we're discussing the two morphisms, because then, of course, the three morphisms fix everything. And so the three morphisms are going to be pictures like the following. So these surfaces embedded in cubes sorry if that's a bit hard to see. It's meant to be on the top surface of the cube, two lines going that way, and on the bottom surface of the cube, two lines looking like a cup and a cap in the Temperley-Lieb diagram, and the mess in between is meant to look like a saddle. Okay, and of course, you have these modulo, these relations, which will be familiar to many. Oh, sorry, I should add one more thing. These three morphisms are allowed to have dots drawn on the surfaces, so we can give the simplest version of this. And you have now these local relations. So here we're really implicitly allowing formal linear combinations of these diagrams, and then we have some ways of rewriting these surfaces. Okay, it's important you never write the numeral 0 in this subject because it's a piece of string. Okay, so what's the point of this? Well, this thing is a categorification of Temperley-Lieb. It's some three category, and the claim is that it's Grothendieck thingy, where the appropriate type of thingy here that you get out when you take the Grothendieck of it is a two category. So the Grothendieck two category of this guy is exactly the Temperley-Lieb that we just described. And the reason for that, of course, is this isomorphism. So instead of an equation that the circle is equal to delta, which now we'll write as q plus q inverse, just as a change of variables, we have an isomorphism circle, which of course remember is now some two morphism of our three categories, so we can say it's isomorphic via three morphisms to, well, I have to cheat a little bit here and do some things that I haven't really admitted I'm doing yet, but that's okay. So it's isomorphic to a direct sum. Ignore the q and q inverses for a minute. It's isomorphic to the direct sum of the object, the empty Temperley-Lieb diagram, with another copy of the empty Temperley-Lieb diagram. So, well, I've done some complicated things here. I've added formal direct sums in my category. So now, just like I said, we had formal linear combinations at this top level. You can sort of always take some category that's linear at the top level and take matrices over that category, which basically means allowing formal direct sums of things at the previous level. That's what this direct sum means. And the q's and q inverses, well, enough of you know about. And those of you don't, I don't want to bother saying. And so what is this isomorphism? Well, let's just draw all the components. So I have to specify some three morphism, and then some inverse three morphism back again. And these are the components. So since this here is a map from one direct summand to two direct summands, it's a little 2 by 1 matrix, 2 columns and 1 row, and here are the matrix entries. And let's just check that this map composed with that map is the identity, and then we also need to check that this map composed with this map is the identity. And so one way round, what do we get? Well, we go from here through to here, so we can either kill off our circle using a dot, and then create the circle again using a disk, or we can kill off the circle just using a disk, and then create it again using a disk with a dot on it. And of course, that's exactly, the relations were exactly designed so that that would be the identity in our, the identity morphism in our 3 category, just by applying the neck cutting relation there. And then the other composition is going to be some morphism from this object back to itself. So it's a morphism from some object with 2 direct summands to itself, so it's some little 2 by 2 matrix. And so we work out the 4 entries of the 2 by 2 matrix by looking at the 4 different paths from this object back to itself. We can either go out here and back in there, so that you create the circle with a disk and then annihilate it with a disk with a dot on it. So the morphism up in the top left entry of this little matrix is a sphere with a dot. And then this entry here is where we come out of the first object but come back to the second object. So that one there is a little blank sphere, and you can fill in the rest. Which of course, exactly by the way the relations were designed, this is just the matrix 1, 0, 0, 1, which is the identity on this object. So we showed that we had this isomorphism in the category. Now I said a slightly stronger claim. So far I've just said that there is this isomorphism in the category, and the slightly stronger claim is that this is really the only isomorphism. And that then gives you the conclusion that the Grothendieck 2 category of this 3 category is exactly Temperley-Lieb. So you have to know that there are no more isomorphisms, there are no more interesting isomorphisms in this category to ensure that when we go down a level, there are no more interesting equations amongst the Temperley-Lieb diagrams. Okay. So that's nice. That's a categorification of Temperley-Lieb. And now what's the connection with link homology? Well, it's not immediate. There's no sense in which the braiding right there on Temperley-Lieb is reflected in this 3 category. You need to do one more thing before the braiding turns up. And this is a familiar and old story, but we need to pass to the homotopy category of this 3 category. So that is, well, we leave the bottom stuff the same, and we replace the 2 morphisms and 3 morphisms with chain complexes in this category. So chain complexes where the chain groups are 2 morphisms and the differentials are 3 morphisms. So we put chain complexes here and chain maps up here. And then there's this formula that is, of course, just sort of the definition of Khovanov homology, which we've managed to take half an hour to get to. So here's there's the saddle morphism from this guy to this guy. This thing is a chain complex in that 3 category. Okay, so you make that definition. And use this de-looping isomorphism we described over here to verify that the 2 sides of each Rademeister move are homotopic. They're chain complexes that are homotopic. And it's really very simple. You just get 2 different looking chain complexes for the 2 different sides of the Rademeister move, and all that you do is repeatedly apply this isomorphism to remove any circles you see, repeatedly throw out any contractible summands of the complex you see, and you get identically the same complex on either side of the Rademeister. So there really is sort of just a proof by simplification on both sides. Okay, so those few boards there then are the way that Temperley-Lieb appears in link homology. Khovanov homology is the link invariant you get from realizing that there is this 3 category that categorifies Temperley-Lieb, and that as long as you pass to the homotopy category, admits something that behaves exactly like a crossing. So, Temperley-Lieb seems to appear in both sides of the story in a very important way. So let's start pointing out the flaws in this story. And see, explain a bit about why this resemblance is pretty superficial. So let's start with the case against there being a connection. So the important thing is that these are 2 essentially different versions of Temperley-Lieb, although I've managed to obscure it reasonably well in giving this very simplified presentation of things. So how do I want to justify that? Well, so Temperley-Lieb appears whenever we have a self-dual object in a category. So what does it mean to say you've got a self-dual object? Well, whenever you've got some object in some tensor category that has a dual, that's saying that you have maps from x dual tensor x to the monoidal unit. I mean, this is what's true in vector spaces. You've got a map from the dual vector space tensor the vector space to the complex numbers, and you've got a map back the other way from the monoidal unit to x tensor x dual. Now, of course, if the object is self-dual, so that is the dual of x is just x itself, we can just erase the stars here. And so when in the presence of a self-dual object, you get a pair of maps like this, and it's very tempting. So these are called evaluation and co-evaluation. And so it's very tempting to draw them. Persist. It's very tempting to draw them like this and this, because of course the rules, when you go look up the axioms for a rigid tensor category or just think about vector spaces, the rules for the evaluation and co-evaluation map are exactly that they satisfy the string straightening axioms. So it's tempting to draw the morphisms like that. However, there are 2 important variants of sort of this setting. X is either symmetrically self-dual or anti-symmetrically self-dual. And there's a difference in the way that the pictures behave. So let's be a little bit more careful in saying that we've got a self-dual object x. Saying that that x is self-dual maybe means that we should say that there's some isomorphism. Let me pick a good shape. Draw a little sideways triangle. So here is some map from x to x dual, which we're thinking of as the map that shows us that x is self-dual. Okay, and we've got another map back from x dual to x. And so, of course, if we're saying x is isomorphic to x dual, we're asking that that these maps are just the identities when you compose them. Okay, similarly the other way around. Okay, well, when you've got this situation, there's something you can look at. You can write down the following diagram. Oops, how do I want my arrows? This way. You can construct this morphism here. So what have we done? Well, we've started with a copy of the object x. Now over here we've used a co-evaluation map to create out of the monoidal unit a copy of x dual and x, then we're using our isomorphism to turn x into x dual, and then we're using an evaluation map over here to cancel those two copies there. And so this is some map from x to x dual, and at least maybe I should have said this earlier. Let's imagine, just for simplicity, we're thinking about the case where x is a simple object. It's only got sort of a one-dimensional space of endomorphisms, which means that we probably should have only a one-dimensional space of isomorphisms from x to x dual. Sorry, that was a bit unmotivated there, but this thing ought to be some scalar multiple of the isomorphism we had to start with. And if you think about it, maybe applying this twice, twisting it again, you can see that this thing has to either be plus or minus the isomorphism you started with. And this is exactly the distinction between the two different ways in which an object can be self-dual. When you write down the isomorphism from x to x dual, when you rotate it by pi, do you get plus the isomorphism you started with or minus the isomorphism you started with? Okay, so what's the relevance of all that for these two Temperley-Liebs? Well, you can probably guess that what I'm going to explain is that the two Temperley-Liebs that appear in subfactor theory and in link homology are really, I think, different versions of Temperley-Lieb, and that's obviously a bad sign. So maybe something to notice here is that when you were in the symmetrically self-dual case, it was fine to do what we'd been doing before and just draw diagrams with unoriented strings, because x was isomorphic to x dual, arrow up was isomorphic to arrow down in just a completely boring way, and you'd lose no information by erasing all of the arrows. Okay, so sort of the Temperley-Lieb we were working with before, the subfactor Temperley-Lieb, and here I mean the normalized version, so that we got rid of that distinction between shaded and unshaded circles. Is the symmetrically self-dual version. Oh, thanks. Okay. But, well, maybe it's not really clear in this version of this Barnatan category. It really looks like the symmetrically self-dual version as well. But, let's maybe just briefly say link homology Temperley-Lieb is really anti-symmetrically self-dual. And there may be two perspectives that you can take on that. One is that link homology is a subfield of representation theory these days, apparently, and there link homology exists because of a categorification of UQSL2, and the fundamental representation of SL2 is certainly an anti-symmetrically self-dual object. So if you believe link homology comes from representation theory, then this is just expressing the fact that the two-dimensional vector space as a representation of SL2 is an anti-symmetrically self-dual thing. And you can see it in the determinant map, giving you those cups and caps. And then maybe the other perspective that suggests this is that when you want to make a functorial version of sort of the SL2 version of Khovanov homology, you really do have to categorify this sort of version of Temperley-Lieb, where you keep track of the isomorphism and which way the isomorphism is facing matters, and you can see that in what I did with some other people in functorial Khovanov homology and what Christian Blanchet did. They're all really showing you that you need this feature. So that's a sort of bad sign. And maybe even worse here is that I had to write normalized here before the Temperley-Lieb that we saw from subfactors was the symmetrically self-dual version. If we were honest with ourselves, normalizing was a bit weird. This is really just yet another version of Temperley-Lieb where which is shaded, and somehow it's sort of even more different than this one. Okay, the other thing that I would say if I had more time, but I don't, is that the other really big difference between the two sides is that root of unity behavior shows up really, really naturally and cleanly on this side, sort of inevitably. Sort of one of Vaughan's first gigantic theorems as a consequence of thinking about Temperley-Lieb was that the index for a subfactor is quantized, and if you're below 4, it's naturally of the form 4 cosine squared pi over n, and that's just an appearance of root of unity behavior there. Whereas on the link homology side, well, I don't know, I get the feeling that root of unity behavior is still a bit elusive. That's a challenge. Okay, so that all said, it's a disaster. They have nothing to do with each other. Let's now end the talk with, I guess, just 15 minutes of dreaming. We'll see what we can do. So this part at the end really is just a bit of a fantasy. I'm going to use it as an excuse to tell you about something really, really cool that Andre Enriquez and Dave Penny, well, especially Andre Enriquez and Dave Penny as well, are working on at the moment, which maybe hints at some deeper connection, but there's really nothing concrete to say in what I'm going to do here. Okay. So let's let me skip one little piece of the talk and start telling you about Andre's amazing idea. So if we want to see some connection with link homology, we want to produce some categorified version of Temperley-Lieb that just sort of springs out at us. And but we want to, as much as possible, follow that sort of simple description I gave of how Temperley-Lieb appeared in subfactor theory, thinking about these bimodules and intertwiners between these bimodules. So where we started before, we had rings, and sort of acting or kind of going between those rings, we had bimodules. And between these, we had intertwiners of bimodules. Now we'll try just going up a level. So we're going to replace our rings with monodal categories or tensor categories. Between those, we'll think about bimodule categories. So for people who aren't familiar with this sort of language, I mean, a monodal category is a category where you can tensor things together and end up back in the category. A bimodule category, say M, between two monodal categories C and D, is some gadget where you can take an object of M and tensor it on the left with an object of C and end up with another object of M. We can tensor it on the right with an object of D and end up with an object in M, and sort of similarly for morphisms. So it's a categorified version of this. But since we've gone up a category level, there's an extra level of structure we can put here. We can talk about functors between bimodule categories, and then we can talk about natural transformations between those. So we might hope to start with some inclusion of monodal categories, look at the bimodule generator with that inclusion, and sort of just see what appears. Of course, to have a hope of getting very far, we'll need very special monodal categories. Just like back here, rings only got us a little bit of the way, and we needed tracial von Neumann algebras to get the rest of the way. And happily, this is exactly what Andre is proposing for us. So Andre Enriquez proposes this notion of bicommutant categories. So what is a bicommutant category? Well, this is a monoidal category, just like a von Neumann algebra to begin with is a ring and then has some extra stuff. Well, what extra stuff does a von Neumann algebra has? A von Neumann algebra has a realization inside bounded operators on Hilbert space. It's a subalgebra of B of H. And so what we want is, as the next piece of data, a functor, a tensor functor from our category C to this gadget called BIM-R, which I'm not going to say anything about, but this is some gigantic, absolutely ridiculous tensor category of all bimodules over this thing called the hyperfinite 2-1 factor. You've got some choice about, actually, maybe you can use the 3-1 instead. But, okay, and this is meant to be our analog, where instead of B of H, bounded operators on Hilbert space, we've got this tensor category of bimodules over this amazing gadget R. And finally, we've got a bit of a confusing thing. We've got that the natural inclusion of C into its double commutant, which I'll have to explain in a moment, is an equivalence of categories. Okay, and this is exactly meant to be analogous to the final condition for a von Neumann algebra, that it's equal to its double commutant. But there's a lot hiding in the notation just there for double commutant. So let me very briefly say that. So here you've got a, if you've ever seen the notion of a Drinfeld center, then you can pretty much follow your nose and reconstruct what I'm about to say. So we have C mapping into BIM R, monoidal categories. The commutant is another monoidal category whose objects are pairs, x and beta. So here, x is some bimodule over R. And now, given such an x, what can you do? Well, you can start with C, and you can tensor. Well, you can tensor on the right with x, your fixed bimodule. And of course, that doesn't end up back in C, because this was just some crazy bimodule. So we're over here in BIM R. Or you can tensor on the left with x, and this is another functor from C into BIM R. And beta here is meant to be a natural isomorphism between those two functors. So you should think here, it's not all those x's that commute with everything in C, it's all those x's along with a specified way of how that x commutes with everything in C. There's 2 bits of data. Okay, once we've categorified, it's not that you commute, you have to say how you commute, and that beta is specifying how you commute. And of course, this C prime has a functor still to BIM R, just by sending the pair x beta to x, and so you can take the double commutant again. It's the sort of gadget that you can take the commutant of. And I'll leave it as a little exercise to unravel from this definition why is a canonical map from C to C double prime. And the condition is that we ask that canonical map is an equivalence. Okay, so we need a little bit more. Well, we needed our algebras to be factors in order to get some of the things we wanted, that the shaded outside circle was a scalar. So what would a factor be? And I'm skating on pretty thin ice here by now, but it's okay, there's only 5 minutes to go. This should probably just be a bicommutant category. Well, just like before with trivial center. But we have to use the appropriate categorified version of center, but happily there's already a notion there. Something that worries me about that statement is that this condition doesn't interact with, only talks about the monoidal category structure on C and doesn't really talk about the interaction with BIM R, which makes me wonder if there's something stupid about that. And then we can talk about a categorified subfactor is meant to be one monoidal category sitting inside another, both of these guys having maps over to BIM R, both of them having being equivalent to the double commutants, and both of them having trivial Drinfeld center. So trivial Drinfeld center, it used to, trivial center for a von Neumann algebra was saying the center was the complex numbers. Now the center is going to be some monoidal category, and we ask that it's the category of vector spaces. Okay, so with all that, what can you do? Well, you can kind of follow your nose at least one step further. There's a nice notion of tensor product. So we can form things like B tensored over the modal category A with B. and that's still some BB bimodule category. And what's the construction here? Well, let's just change letters for a moment. Let's say I've got M and N module categories over C. Here the objects are just pairs, an object of M and an object of N, and the morphisms from some pair Mn to another pair M prime N prime can describe in the following way. Well, what you should do is draw a picture like this. There's M and N and M and M prime and N and N prime, and in the middle here a little edge labeled by C, some object of the tensor category C you're doing the tensor product over, and now you just fill in this guy here with some morphism from M, and this guy here some morphism from G. This is some big collection of diagrams, and you can compose them by stacking these diagrams vertically, and you add a relation. Just like when you take the tensor product of two bimodules over a ring, you add a relation. And the relation just says that you can think of this diagram here. So now these guys, the big blobs on the left and right, are labeled by morphisms from your module categories. The blob in the middle is labeled by a morphism from the category we're tensoring over. And the rule is just you can think of it as either glommed together that way or glommed together that way. Because M is a module category, we can push this blob in here, and now this is a picture of this form. Or we can push this little blob in here using the fact that N is a module category, and now this is another picture of this form, and those should be equal. Okay, so there's some definition of tensor products. And it's actually pretty easy to see that the things that come for free in the pre-categorified world for just rings still come for free. There is a natural map of bimodule categories from this tensor product to this one. And it's really just that in this one, the morphisms look like two morphisms from B, but with the restriction that you're only allowed to move morphisms from the subcategory A across the middle. And the map here is just forgetting that restriction and thinking of it as one big morphism from B. Okay, so you get the same things that you got for free for the ring case before, and then I've got absolutely no idea if you get the extra bits. So this is the part where in our little mathematics dream, we're glad we're dreaming because flying usually hurts, and we can wonder what else we get. But what you can see, you can still see that sort of some basic thing. This fact that this guy was the number one in the ring world. You again see that that's very naturally the identity functor on these bimodules. But you can now sort of start to wonder, well, if we could construct the functors associated to these pieces, what would this be? So this would be some map from curly B as a BB bimodule back up to, and then finally using multiplication. So this is the part we know nothing about, and this is the multiplication. Well, this is now going to be some functor of bimodule categories, and we might ask, just are there natural transformations? Either to the identity or back again, and maybe just like in the subfactor case where this guy was some scalar multiple of the identity, we might see that if there are enough nice natural transformations here, we might in some way be able to take this functor and decompose it maybe as a direct sum of simpler functors that are maybe built out of the identity. And that would be categorifying the relation that here this guy was q squared plus 2 plus q to the minus 2 times the empty picture. We might hope to turn this into some isomorphism of this functor into a direct sum of other ones. Okay, but at that point, the dream stops, you start to wake up, and you're left with just a dim memory that all of this was nonsense. Okay, I think that's all I've got to say. But I love bicommutant categories. I think they're really cool, and I hope that Andre manages to prove cool things about them in the next year or two. Thanks.
Questions about Scott's dream?
Very nice, yeah.
So you have this tensor function from C into BIM-R. So wouldn't it be simpler to just think of subcategories of BIM-R? Are there more examples that motivate wanting to take things that are outside BIM-R? Like that? Generalized?
Yeah, that's a good question. I remember asking Andre this at some point and forgetting the answer. Yeah, sorry.
I mean, the commuton is different if you look at the, like, now a commuton is a structure and not just a property, right? It doesn't make sense to say you can
Yeah. I mean,
would actually if you had
yeah, I mean, this thing here, this C prime here just isn't a, this C prime here just isn't a subcategory of BIM-R. I mean, it's the object here pairs an object of BIM-R together with extra data. So if we expect to take the second commutant, thank you, Noah, then you really have to allow that generality. Great. Yeah.
All right, well, let's thank Scott for his